guys, today is our first video about Vivado HLS. This training is a training on demand on one of our subscribers, and well, today we're going to learn how to use C or System C languages to synthesize Verilog or VHDL code. The main idea of Vivado HLS is to accelerate the process of transforming your algorithm in C, C++ or System C into an IP core inside your FPGA. Hope you guys like it. I'm going to show to the board what topics we are going to cover in this whole course, and well, let's start. I really hope that you guys are going to enjoy it a lot. Ciao, ciao. So, Vivado HLS. HLS stands for High Level Synthesis. Okay, it's basically using C++ or C or System C or any high level language. For instance, could be MATLAB, not with Vivado HLS by the way, to Verilog or VHDL IP core plus test benches. These plus test benches I'm going to explain in a little while. Okay? Well, Vivado HLS does no magic. Basically, it's going to get your algorithm in C++, for instance, and it's going to extract a data path and a control unit based in your code. Okay? In previous videos, for instance, the FPGA introduction, we learned how to do exactly this by hand. Okay? What are the topics that we are going to learn in this course? First, the introduction, which does not end here in this first video. Code simulation, which means use your test bench written in C, use a program written in C to test the generated VHDL or Verilog code. Okay? We're going to learn how to instantiate IPs that use AXI-Lite cores, AXI-Stream cores. Okay? We're going to learn how to use AXI master as well. We're going to learn how to do loop or function optimization. There are some set of programs in Vivado HLS that allows you to control how the hardware will be generated. So we're going to lose some time explaining this because this is where the magic relies on Vivado HLS. This is how you can really accelerate your algorithm, for instance, compared to a microcontroller or microprocessor or whatever. Okay? We're going to learn how to do image processing with Vivado HLS. First by hand. Okay, we're going to learn how to do some kind of 2D convolution or the basic morphological operations, and we're going to end up with the OpenCV extension for Vivado HLS. Okay guys, Vivado HLS cannot just get any C or C++ code and generate Verilog or VHDL code from it. Okay, there are some limitations on Vivado HLS. Okay. So, for instance, Vivado HLS, the C++ code that you're going to generate, the IP core, it cannot have dynamic memory allocation, okay? So, no malloc, free, new or delete, okay? Vivado HLS does not support STD or boost, probably even because of this dynamic memory allocation limitation. So, no STD. No file I/O, basically no system calls, okay? No printf, no exit, you cannot, okay? Basically you cannot. Avoid recursive functions as well, okay? This is a limitation of Vivado HLS. There are some other kind of more generic limitations, okay? When maybe Vivado HLS is not the best tool for doing the job. Okay, in a lot of cases it is, but sometimes not. Okay, it's not a single hammer for every whatever. Okay, so the generated code is not the most readable. Okay, in the first lab we're going to do the division algorithm, and you guys can compare the readability of the code that you wrote by hand in the FPGA playlist, the training, and the generated code from Vivado HLS. Okay, so it's kind of not made for you to generate the code, read the code, and say, this is how it does. No, it's not. Okay. Sometimes you want something smaller than the pattern control unit and data path. sometimes you really don't want a finite state machine. You want something more simple. For instance, we're going to learn how to do 2D convolution in Vivado HLS, and we're going to see the generated code, not even the generated code, we're going to see the amount of resources that it uses, and sometimes you can do the same thing with less resources and a little bit faster. So basically, if you want a little bit more control, if you want more control on the generated code, in this case Vivado HLS is not the tool for the job. Basically, the Vivado HLS can be thought as the main tool that the software engineer will enter in this FPGA world. I mean, it's way more easy for a software engineer to change his code to do not use dynamic memory, use all memory statics, avoid STD and stuff like that, really changing just the C or C++ level of your code and generate a hardware accelerator, okay? But sometimes you want more control, and the Vivado HLS is not the tool for doing this. Let's talk a little bit about the interfaces generated by the Vivado HLS. Just to start, the function is the entry point of Vivado HLS. When you start a project in Vivado HLS, one of the first things that you need to do is to say to Vivado HLS, look, this is the function in which I want to generate a hardware from. Okay? So, function is an entry point. In our case here, we have a function called subcalc, okay, which has as input parameter A and B, and as output a pointer to C, okay. The parameters of the entry point function is going to define what will be the ports of your generated IP core. So for instance, here we have double A and B. These are going to become bit vectors. By the way, double maps to 64-bit vector in Verilog or in your IP core. So here as input we have A and B, and as output we have a pointer to C, okay, which is going to be mapped out as well as a bit vector of 64-bit with another signal called API VLD, which stands for API valid. So it means that this signal will be asserted when you have a valid output on C. Okay? By default, every IP core generated by Vivado HLS is going to have those signals here, okay? Which is going to be the API start, API reset, API clock, API idle, API done, and API ready. The reset and clock is normal, every sequential circuit is going to have, as everything that is generated by Vivado HLS is going to have a finite state machine and a data path. All circuits generated by Vivado HLS are by default sequential, are obligatory sequential. Okay? So let's talk a little bit about those signals. API start is going to be asserted when you want to begin the computation. Okay? API idle is an output, is going just to say that the computation has not been started yet. API ready, this can appear if your circuit has pipeline, is something that you're going to learn in the future. It's just to indicate that the core is ready to receive another input, okay? And API done is just to indicate that the computation has been finished. In next videos we're going to see also that if you use a parameter as an array, this is going to instantiate a memory interface or a FIFO interface. But to this first video, let's keep stuff simple and let's go to the basics and learn the concepts, okay? Just to finalize and before we start the lab, we're going to show the workflow that you normally use in Vivado HLS, okay? The first thing that you do is to define your function or your algorithm, okay? After you define your function and your algorithm, you also create a program that uses your algorithm, okay? Which leads us to the second step. You simulate your algorithm as compiled code, which is going to simply to compile your algorithm in your computer and execute as an executable in your computer, okay? Then, Third step, you synthesize, okay? You're going to convert your algorithm from C to an HDL language, okay? Normally in this step, you need to change, just go back and remember that for instance, your algorithm cannot have recursion, it cannot have, for instance, dynamic memory allocation. All your pointers need to point to statically defined arrays and stuff like this, okay? So you can lose a little bit of time to prepare your algorithm to be synthesizable in terms of FPGA. And then after this step is done, you co-simulate. What this means? Here at this step you simulate your compiled code, okay? Here you simulate the HDL generated code. So we're going to use, for instance, the Vivado simulation engine or Model Sim or Orchestra Sim that is going to work with your test program and is going to verify if the inputs given by your test program gives the same output as your original algorithm. Okay, so this is the workflow that you should follow normally when you're working with Vivado HLS. This first lab, we're going to show the same algorithm that was the final algorithm that we showed on the last video of the FPGA training. Is the divide algorithm. So we are simply going to write the divide algorithm in C, and we're going to use Vivado HLS to generate an IP core from this code in C. Okay guys, we start by creating our project, okay, in Vivado HLS. We just naming here the project, and as we said, one of the important steps, the first step is basically to choose your function entry point. Here we just name a function that's going to be our entry point, which by the way is the divide algorithm, and here we just say max and x. Here we are going to choose the board that is going to be our reference. In our case is the Z board, is where we are going to do the most of our labs, okay? And after this is done, a project will be created, and now you create the CPP file that is going to be part of your, that's going to include your function, okay? Here we just put a name, can be any name. .cpp is going to make Vivado HLS assume that is C++ code. So here, let's pay attention not only on the code, but the most important thing to notice is the header of the function. Okay, the header of the function, the header of your entry level, the header of your entry point function, it is that where you're going to define which port your IP core is going to have. In our case, N and D, the inputs, Q and R, the outputs. Okay, Q and R we are defining as pointers. Okay. So when we call this function, we're going to give the address of a variable. This will be instantiated as an output port in your IP core. Okay. Here we just comment a little bit the code for helping understand how it works, but it's really simple. You can just have a look on the wiki. The divide algorithm is quite known, and there is nothing fancy about it. You may have some difficulties with the bit manipulation in C, but it's quite simple. I just copy and paste some code from Stack Overflow. This is the simplest way to do. The important point is just to understand that we are using a C code, a normal C code, nothing fancy at all. And now we are creating a program that is going to exercise this function. Okay? It's a simple program. We just call the function with some parameters and we want to get the result. Okay? By the way, when we do the co-simulation, this is going to be our test bench. The Vivado HLS will also create a test bench over your test program. Okay? So now that your program, our test program is complete, we're going to compile this code with our function and execute it to see if it's working as expected. Okay, this is the first level of test. Check if your algorithm, your C code is a valid C code, if it's really working, and it is. Okay, we divide 8 by 3, the quotient is 2 and the rest is also 2. And if you divide 4 by 2, quotient is 2 and the rest is 0. So it's working as expected.
Okay, we can launch the debugger as well if needed. Just well, to debug. Okay, so basically, if you want to step line by line, see how the variables are changing in your code, you can do that just by using the debugger. By the way, this is a normal. If you are used to use Eclipse CDT, there is really nothing new there. Okay, it's just Eclipse with C++ compiler. Okay, and well, after this is working, your algorithm is working as expected. Now should be time that you should synthesize this code. Basically, you're going to ask Vivado HLS to create HDL code from your C++ top function. Okay, is this green button on top, and we are basically letting Vivado do everything with the defaults. So this is the synthesis report. Here we can have information about timing, the latency of your code and stuff like this, the resources used, and now in the bottom you can see the interfaces. Okay, so as a rule of thumb, scalar parameters are going to be bit vector. Okay, pointers are going to be also bit vectors, but depending on how you use your pointer, it can create two ports, one from input and one from output. Okay, this is the generated HDL code, Verilog by the way. As I said, it's kind of cryptic. Okay, the code is really not easy to understand. It's not. I mean, it's really generated code. It's kind of really machine code. If you take a look, there is a lot of constants and stuff like this. Basically, the idea is that you should not take care about the generated code. You should believe that the code is going to work as expected and accept it. Okay, it's a different way to develop. Now we are going to co-simulate, which means we are going to still use our test program, but we're going to exercise the generated VHDL code, the generated Verilog code with our test. So basically, you're going to confirm that the generated code works exactly as your C code that you develop that you develop in the first place. Okay. Here just showing how we can dump the waveform. So this is useful because then you can open, for instance, QuestaSim and see the waveform. By the way, QuestaSim is licensed. Huh? If you have Vivado HLS alone, you need to use the Vivado simulator, which is a little bit more, I mean, way more slow than QuestaSim. But sometimes, depending on your company or your job, you really cannot have all the license available. Okay, so this is just the path that you normally have generated is in sim. Okay, everything that is generated for simulation is in sim. There is a directory sen for the synthesized code, and here we're just going to open this waveform in QuestaSim, and we're going just to display the signals. Okay, the important signals that you can see here are the start, done, and idle. Also the input ports for N and D, and the output ports Q and R. As we use pointers and we read this pointer for Q and R, we actually creating two ports for every output variable, one from input and other for output. Okay, guys, basically for an introductory video on Vivado HLS, that's it. Main idea: convert C or C++ entry function into an IP core that is really accelerate the way that you port algorithms to FPGAs. So, for instance, for the point of view of a software engineer, this is really cool. This is really a bridge between software and hardware. As I said before, there are cases that are really good to use. There are cases that are not. Our idea as engineers is know a lot of tools and also know when to use the tool or not. So this is a new tool in your bag of tools. So it's a cool one. Okay, so see you guys in the next video, and I hope you guys enjoyed. Okay, so ciao ciao, and see you soon.